An electron can slam through a particle accelerator carrying the energy of a flying mosquito. It can sit quietly inside a hydrogen atom, locked into a state so low in energy that it cannot fall any further. It can leap between levels and release a photon that crosses the entire universe. But here is what almost nobody stops to ask. Where did that energy actually come from? Because an electron is not a tiny battery. It does not carry a hidden fuel tank. It does not generate energy on its own. And yet, every measurement physicists have ever made confirms the electron has energy. Sometimes a little, sometimes an extraordinary amount. The answer involves mass itself, invisible fields, quantum rules with no everyday equivalent, and a chain of transfers that reaches back to the very fabric of the universe. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Energy. You use the word all the time. You talk about having energy when you wake up rested. You say a cup of coffee gives you energy. You hear about energy bills, energy drinks, energy crises. The word is everywhere. And in everyday life, you treat energy almost like a substance, like fuel in a tank. Something you have a certain amount of. Something that gets used up. Something you can run out of. And for daily purposes, that way of thinking works fine. Your car burns gasoline, and the energy stored in the chemical bonds of that fuel gets converted into motion. Your body breaks down food, and the energy stored in those molecules powers your muscles, your brain, your heartbeat. In everyday life, energy feels like stuff, a quantity of something real and tangible that flows from one place to another. But when you step into the world of physics, especially when you start asking questions about electrons and fundamental particles, that everyday picture of energy breaks down completely. Because energy, at its deepest level, is not a substance. It is not a fluid stored inside a container. It is not something an electron carries the way a truck carries cargo. Energy is a property. It is a measurable quantity that describes the state of a system. That distinction sounds subtle, but it changes everything about how you should think about where an electron gets its energy. Think about it this way. A cup of hot coffee has a high temperature, but you would never say the coffee contains temperature the way it contains liquid. Temperature describes the state of the molecules in the coffee, how fast they are vibrating. You measure it. You can change it, but you cannot scoop temperature out of the coffee and put it in your pocket. Energy works the same way at the fundamental level. It is a measurable property of a physical system, not a material stored inside that system. This is critically important because one of the most common mistakes people make when thinking about electrons is imagining that the electron has a little reservoir of energy hidden somewhere inside it. It does not. What the electron has are properties, mass, motion, position within a field, quantum state, and those properties determine how much energy it contributes to whatever system it is part of. Now, with that understanding in place, let's talk about the first and most fundamental source of an electron's energy. The energy that comes from simply existing. The energy that the electron possesses even when it is completely alone, completely still, floating in empty space with nothing around it and nowhere to go. This is called rest energy. And understanding it requires one of the most famous equations in all of science. An equation written by Albert Einstein in 1905 that changed our understanding of the universe forever. Einstein showed that mass and energy are not separate things. They are two expressions of the same underlying reality. A particle that has mass automatically has energy, even if it is not moving, even if it is not interacting with anything, even if it is doing absolutely nothing. The relationship between mass and energy is described by the equation E equals mc squared. You have probably seen this equation before. It might be the most recognized equation in history. But most people who know the equation do not fully understand what it means. So let's break it apart carefully, because this equation is the foundation of everything we are going to explore tonight. E stands for energy. That is what we are trying to figure out. How much energy does a particle have simply because it has mass? The M stands for mass, not weight, mass. Weight depends on gravity. Your weight on the moon is different from your weight on Earth. But your mass is the same everywhere. Mass is a fundamental property of matter. It is a measure of how much stuff is there, how much resistance the object has to being accelerated. And C stands for the speed of light. Light travels at about 300,000 kilometers per second. That is roughly 670 million miles per hour. It is the fastest speed anything can travel in the universe. And in this equation, you do not just multiply mass by the speed of light. You multiply mass by the speed of light squared. In the standard units physicists use, that is 300 million meters per second. Multiply it by itself, and the result is 9 times 10 to the 16. That is 90 quadrillion in everyday language. So even if the mass is tiny, even if it is the smallest amount of mass you can imagine, when you multiply it by 90 quadrillion, you get a significant amount of energy. This is what makes the equation so extraordinary. It tells us that mass is incredibly concentrated energy. A tiny amount of mass corresponds to an enormous amount of energy. This is not a theoretical abstraction. It is a measured fact. Nuclear power plants work because of this relationship. When uranium atoms split, the fragments have slightly less total mass than the original atom. That missing mass has not vanished. It has been converted into energy, released as heat, which boils water, which turns turbines, which generates electricity. The sun works the same way. Deep inside the sun, hydrogen nuclei fuse together to form helium. The helium nucleus has slightly less mass than the hydrogen nuclei that formed it. That missing mass becomes the light and heat that crosses 93 million miles of space to warm your face on a summer afternoon. Every star you see in the night sky is powered by this relationship. Mass becoming energy, E equals mc squared, playing out on a cosmic scale across the entire universe. Now, let's bring this back to the electron. An electron has mass, not much mass. The electron is one of the lightest particles that exists. Its mass is about 9.109 times 10 to the negative 31 kilograms. That number is so small that writing it out would require 30 zeros after the decimal point before you reach the first significant digit. It is unimaginably tiny. If you put a trillion electrons on a scale, they would weigh about 1,000th of a gram. You would not even notice them. But even this incredibly tiny mass, when you multiply it by the speed of light squared, gives you a real, measurable amount of energy. The rest energy of a single electron is approximately 0.511 mega electron volts. Now, a mega electron volt is a unit of energy that physicists use when they talk about particles. It is very small compared to everyday energies. You could not power a light bulb with it. You could not heat a cup of coffee. But in the world of subatomic particles, 0.511 mega electron volts is significant. It sets a baseline. It defines what the electron is. Here is what this means in practical terms. Imagine you could somehow isolate a single electron and place it in perfectly empty space. No other particles nearby, no electric fields, no magnetic fields, no photons, no gravity, nothing. Just the electron, alone, completely at rest. Even in this scenario, the electron would still possess energy. 0.511 mega electron volts of energy, locked into its mass. This is not energy the electron is using. It is not energy the electron is spending or consuming. It is energy that is equivalent to the electron's mass. The mass is the energy, and the energy is the mass. They are the same thing measured in different units, the way that inches and centimeters are different units for the same underlying quantity of length. This rest energy is the absolute minimum energy an electron can ever have. You can add energy to an electron by accelerating it, by placing it in a field, by putting it inside an atom. But you can never take away its rest energy without destroying the electron itself. If you somehow converted all of the electron's rest energy into another form, if you annihilated its mass entirely, the electron would cease to exist. And this actually happens. When an electron meets its antimatter counterpart, a positron, the two particles annihilate each other. Both particles vanish completely. Their combined mass, roughly 1.022 mega electron volts worth of rest energy, converts into photons. The mass is gone. The particles are gone. But the energy remains, carried away by the photons. Energy is conserved. It does not appear from nothing, and it does not vanish into nothing. It transforms from one form to another. Now you might be wondering something. If the electron's rest energy comes from its mass, where does the mass itself come from? Why does the electron have mass at all? Why does it have this particular mass and not some other value? This is one of the deepest questions in modern physics, and the answer, as far as we currently understand it, involves a field that fills the entire universe. A field that was predicted in the 1960s and confirmed in 2012. The Higgs field. To understand the Higgs field, you first need to understand what a field is in physics. A field is not a fence around a piece of land. In physics, a field is something that has a value at every point in space. Think of temperature. At every location in this room, there is a temperature. Some spots might be warmer, some cooler, but every point has a temperature value. Temperature fills the room like an invisible map of values. A field in physics works similarly. It fills all of space, and at every point it has a particular value or strength. Gravitational fields, electric fields, magnetic fields, these are all examples of fields that fill space and affect particles that pass through them. The Higgs field is different from most other fields in one crucial way. Most fields have a value of 0 in their lowest energy state. When nothing is happening, when there are no particles around, most fields are turned off. They are at 0. The Higgs field is not like that. In its lowest energy state, the Higgs field has a non-zero value everywhere. It fills all of space with a constant non-zero presence. You are immersed in the Higgs field right now. So is every electron, every proton, every particle in your body. The Higgs field is everywhere, always, with a non-zero value. And this is what gives particles like the electron their mass. As an electron moves through space, it interacts with the Higgs field. This interaction is continuous. It is happening right now for every electron in existence. The strength of this interaction determines how much mass the particle acquires. Particles that interact more strongly with the Higgs field have more mass. Particles that interact weakly have less mass. And particles that do not interact with the Higgs field at all, like photons, have no mass whatsoever. This is why photons are massless and travel at the speed of light, while electrons have mass and always travel slower than light. The electron's interaction with the Higgs field is relatively weak compared to heavier particles. The top quark, which is the heaviest known fundamental particle, interacts with the Higgs field much more strongly. Its mass is about 340,000 times larger than the electron's mass. Both particles get their mass from the same field, but the strength of the coupling is different. This coupling strength is called the Yukawa coupling, and for the electron, it is a very small number. Physicists can measure this coupling. They can predict its effects, but here is an honest admission. Nobody knows why the electron's Yukawa coupling has the particular value that it does. The standard model of particle physics, which is the most successful theory of fundamental particles and forces ever constructed, does not explain why the electron has this specific mass. It simply takes the measured value as an input. The mass of the electron is one of the fundamental constants of nature, a number that defines how the universe works, but that no current theory can derive from first principles. The Higgs field was first proposed in 1964 by several physicists working independently. Peter Higgs in Edinburgh published a paper describing a mechanism by which particles could acquire mass through interaction with a new field. Around the same time, François Englert and Robert Brute in Brussels proposed essentially the same idea. So did Gerald Guralnick, Carl Hagen, and Tom Kibble in London. All of them were trying to solve a specific problem in particle physics. The equations of the standard model seem to require that certain particles have no mass, but experiments clearly showed that these particles do have mass. The Higgs mechanism solved this contradiction by introducing a field that permeates all of space and gives mass to particles through interaction. For nearly 5 decades, the Higgs field remained a theoretical idea, a beautiful solution to a mathematical problem, but one that had not been directly confirmed by experiment. That changed in 2012 when physicists at CERN, the European Organization for Nuclear Research near Geneva, announced the discovery of the Higgs boson. The Higgs boson is a particle associated with the Higgs field, in the same way that a photon is a particle associated with the electromagnetic field. The discovery was made using the Large Hadron Collider, the most powerful particle accelerator ever built. A circular tunnel about 27 kilometers in circumference, buried beneath the border of France and Switzerland. Inside this tunnel, protons are accelerated to speeds very close to the speed of light and then smashed together. The collisions produce showers of new particles, and buried among those showers, extremely rarely, a Higgs boson appears for a fleeting instant before decaying into other particles. The mass of the Higgs boson turned out to be about 125 giga-electronvolts, roughly 244,000 times the mass of the electron. Peter Higgs and François Englert were awarded the Nobel Prize in Physics in 2013 for their theoretical prediction, nearly 50 years after they first proposed it. Now, here is something absolutely critical that you need to understand about the Higgs field and energy. The Higgs field gives the electron its mass, and that mass corresponds to rest energy through E equals mc squared. But the Higgs field is not pumping energy into the electron. It is not acting as some kind of cosmic power station that continuously feeds energy to every electron in the universe. This is a misconception that you will sometimes encounter in popular science descriptions. People hear that the Higgs field gives particles their mass, and they imagine the Higgs field as a source of energy, like a battery that keeps particles charged up. That is wrong. The Higgs field gives the electron a property, mass. Once the electron has that mass, the corresponding rest energy is simply a consequence of what mass is. The Higgs field does not need to keep providing energy for the electron to keep having mass, any more than the ocean needs to keep providing wetness for water to remain wet. The property is intrinsic once established through the interaction. The Higgs field is in its lowest energy state. It is not excited. It is not radiating. It is not transferring usable energy to particles. It is simply there, with its non-zero value, and particles that interact with it have mass as a result. Think of it this way. Imagine you are walking through waist-deep water. The water slows you down. It resists your motion. You are harder to accelerate and harder to stop. In a loose analogy, the Higgs field does something similar to particles. It creates a resistance to acceleration, which is what mass is. But the water is not giving you energy. It is not charging you up. It is simply changing how you move through the environment. The Higgs field similarly changes how particles move through space-time, giving them the property of mass. The energy associated with that mass is a consequence of the relationship between mass and energy discovered by Einstein, not a continuous donation from the Higgs field. This clarification matters because it addresses a fundamental question about conservation. If the Higgs field were somehow supplying energy to every electron in the universe continuously, where would that energy come from? The answer is that it would violate conservation of energy, one of the most sacred principles in all of physics. Energy cannot be created from nothing. The Higgs field is not creating energy. It is creating a property, mass, and the energy associated with that mass is simply part of how mass and energy relate to each other in our universe. Let me bring all of this together. An electron has energy even when it is doing absolutely nothing. This energy is called rest energy. It equals the electron's mass multiplied by the speed of light squared. For a single electron, this comes out to about 0.511 mega electron volts. The electron has this mass because it interacts with the Higgs field, an invisible field that fills all of space with a non-zero value. The strength of the interaction determines how much mass the electron acquires. But the Higgs field is not an energy source. It is not continuously feeding energy to the electron. It gives the electron its mass, and the rest energy follows from the fundamental relationship between mass and energy. That rest energy is the absolute baseline, the minimum energy the electron will ever possess. You cannot reduce it without annihilating the electron entirely. It is the energy of simply being. And this is the starting point for everything else we are going to explore tonight. Because rest energy is only the beginning of the story. An electron sitting still in empty space is interesting, but electrons rarely sit still. They are almost always doing something. They accelerate through electric fields, they spiral in magnetic fields, they exist bound inside atoms in specific energy states, they collide with other particles, they absorb and emit photons, and every one of those processes involves energy being added to or taken from the electron's total energy budget. But none of that additional energy comes from inside the electron. None of it is stored in some hidden internal reservoir. Every bit of energy beyond the rest energy comes from somewhere else, from an external field doing work, from a photon arriving with a precise amount of energy from a collision transferring momentum. The electron does not generate its own energy. It receives energy from the systems it interacts with, and it gives energy back to those systems when conditions change. This is the chain we are going to follow. Mass gives the electron its baseline energy. Interactions with fields and other particles add to or subtract from that baseline. Quantum rules dictate which energy states are allowed and which are forbidden. And through it all, every joule, every electron volt, every last scrap of energy is accounted for. Nothing appears from nowhere. Nothing vanishes into nothing. The universe keeps its books perfectly balanced. So the next time someone tells you that an electron has energy, you can ask them a better question. Which energy? The rest energy from its mass? The kinetic energy from its motion? The potential energy from its position in a field? The quantized energy from its state inside an atom? Because the answer changes depending on which energy you are asking about. And understanding that distinction, understanding that the electron's energy is not one mysterious quantity but several physically distinct contributions, is the key to understanding what an electron really is. So now you know the baseline. An electron possesses rest energy simply because it has mass. That energy is locked in, permanent, inseparable from the electron's existence. 0.511 mega electron volts, courtesy of the relationship between mass and energy that Einstein uncovered more than a century ago. But here's the thing. Rest energy is only the floor. It is the minimum. In the real universe, electrons almost never sit still in empty space doing nothing. They move. They accelerate. They exist inside materials, inside atoms, inside electromagnetic fields that push and pull on them constantly. And when an electron moves, it carries additional energy beyond its rest energy. Energy that does not come from the electron's mass. Energy that comes from somewhere else entirely. To understand where that additional energy comes from, we need to talk about two deeply connected concepts: kinetic energy and potential energy. And together, these two ideas explain almost everything that happens to electrons in your everyday life. From the electricity flowing through the wire that powers the device you're using right now, to the lightning bolt that splits the sky during a thunderstorm, to the beam of electrons that used to paint the picture on old television screens. Let's start with kinetic energy because it is the simpler of the two. Kinetic energy is the energy of motion. Anything that moves has kinetic energy. A truck rolling down a highway, a baseball flying through the air, a molecule vibrating in warm air, and an electron hurtling through a particle accelerator all have kinetic energy. The faster something moves, the more kinetic energy it has. This is intuitive. You know from experience that a fast-moving car hits harder than a slow-moving one. A bullet is dangerous, not because it is heavy, but because it is fast. Speed means energy. For everyday objects, the kinetic energy is calculated with a simple formula. 1/2 times the mass times the speed squared. Double the speed, and you quadruple the kinetic energy. Triple the speed, and you get 9 times the kinetic energy. The energy grows quickly as speed increases. This is why highway accidents at high speed are so much more destructive than low-speed fender benders. The energy involved goes up dramatically with speed. For electrons at everyday speeds, this same formula works fine. But there is a subtlety we will deal with later. When electrons approach the speed of light, The simple formula breaks down and you need Einstein's relativistic equations instead. For now though, let's focus on the basic idea. An electron that is moving has more total energy than an electron that is sitting still. The extra energy is kinetic energy. And the faster the electron moves, the more kinetic energy it carries. But here is the crucial question. Where does that kinetic energy come from? The electron did not just spontaneously decide to start moving. Something had to push it. Something had to accelerate it. Something had to do work on it. And in the case of electrons, that something is almost always an electric field. An electric field is a region of space where an electric charge feels a force. If you place an electron in an electric field, the electron experiences a push. It starts to accelerate. And as it accelerates, it gains kinetic energy. This is not magic. The energy comes directly from the field. The field does work on the electron, transferring energy from the field to the electron in the form of kinetic energy. This is exactly the same concept as a ball rolling down a hill. Gravity does work on the ball, and the ball speeds up. The ball gains kinetic energy, and that energy comes from the gravitational field. Replace gravity with an electric field, and replace the ball with an electron, and you have the same physics. Let's make this concrete. Imagine you have two metal plates, one charged positively and one charged negatively, with empty space between them. This creates a uniform electric field in the gap between the plates. Now you place an electron near the negative plate. What happens? The electron is negatively charged. It is repelled by the negative plate and attracted toward the positive plate. The electric field pushes the electron from the negative plate toward the positive plate. The electron accelerates. It moves faster and faster as it crosses the gap. By the time it reaches the positive plate, it has gained a significant amount of kinetic energy. Where did that energy come from? From the electric field between the plates. And where did the field's energy come from? From whatever source of electricity charged the plates in the first place. Maybe a battery, maybe a generator, maybe a solar panel converting sunlight into electrical energy. The chain of energy transfers is unbroken. Nothing appeared from nowhere. The battery's chemical energy became the electric field's energy, which became the electron's kinetic energy. Every link in the chain is accounted for. This is a good moment to talk about a word you hear all the time in everyday life but might not fully understand in terms of physics. Voltage. When someone says a battery is 12 volts or a wall outlet is 220 volts, they are describing a quantity that is directly related to the energy we have been discussing. Voltage is energy per unit of charge. Specifically, 1 volt means 1 joule of energy for every coulomb of charge that moves through the circuit. A 12-volt battery gives each coulomb of charge 12 joules of energy as it passes from the negative terminal to the positive terminal. A 220-volt outlet gives each coulomb 220 joules. This is why higher voltage means more energy available to do work. A 220-volt outlet does not necessarily push more electrons through the wire than a 12-volt battery, but it gives each electron more energy as it passes through the circuit. Think of it like a water slide. The height of the slide determines how much energy each unit of water gains as it falls. A taller slide gives each liter of water more kinetic energy at the bottom. Voltage is the electrical equivalent of that height. It tells you how much energy the field gives to each unit of charge. And notice what this means. The energy is coming from the field, not from the electrons. The electrons are the carriers. They pick up energy from the field established by the battery or generator, carry that energy through the circuit, and deliver it to whatever device is connected. A light, a motor, a heater. The electrons are like delivery trucks. They carry the payload, but they did not create it. The battery created the voltage, the field provided the energy, and the electrons transported it. This is exactly how particle accelerators work, just scaled up to extraordinary levels. A particle accelerator is essentially a machine that uses electric fields to push electrons or other charged particles to higher and higher speeds. The concept is the same as the two charged plates, but the engineering is vastly more sophisticated. In a linear accelerator, the electron passes through a series of structures that create electric fields. Each structure gives the electron a small push, adding a bit of kinetic energy. By stringing together thousands of these structures in a long straight line, physicists can accelerate electrons to speeds that are almost unimaginably fast. The Stanford Linear Accelerator Center, known as SLAC, used a linear accelerator about 3.2 kilometers long to accelerate electrons to energies of about 50 giga-electron volts. That is 50 billion electron volts. Remember, the electron's rest energy is only 0.511 mega-electron volts. At 50 giga-electron volts, the kinetic energy the accelerator pumped into the electron is roughly 100,000 times larger than the rest energy the electron was born with. The electron is moving at 99.9999999% of the speed of light. Almost, but not quite, as fast as light itself, and all of that kinetic energy came from the electric fields inside the accelerator, which came from the electricity powering the machine, which came from power plants burning fuel or capturing renewable energy. The electron did not produce that energy. It received it, joule by joule, from the fields that pushed it along the 3-kilometer-long machine. Circular accelerators, like the ones at CERN, work on a similar principle. But instead of a straight line, the particles travel in a circle, passing through accelerating structures again and again. Each lap adds more energy. Magnets bend the particles' paths into a circle so they can keep passing through the same accelerating structures. The Large Hadron Collider, the most powerful accelerator ever built, pushes protons to energies of about 6,500 giga-electron volts. The concept is the same as the two metal plates we talked about. Electric fields do work on charged particles. The particles gain kinetic energy. Scale it up and you get the most powerful machines humans have ever constructed. But you do not need a particle accelerator to see electric fields doing work on electrons. It happens all around you, every moment of every day. When you flip a light switch, you close a circuit, and an electric field is established at the wire. That field pushes electrons through the wire. The electrons gain kinetic energy from the field, then lose it again as they collide with atoms in the wire. Those collisions transfer the kinetic energy to the atoms, making them vibrate faster, which is what we experience as heat. In an incandescent light bulb, the wire gets so hot that it glows, converting the electrical energy into light. The original energy came from the power plant. It was transferred to the electric field, from the field to the electrons, from the electrons to the atoms in the wire, and from those atoms into light and heat. Every step is a transfer. Nothing is created from nothing. Lightning is another dramatic example. During a thunderstorm, charge builds up in clouds. The bottom of a cloud becomes negatively charged, and the ground beneath it becomes positively charged. This creates an enormous electric field between the cloud and the ground. When the field becomes strong enough, it tears electrons away from air molecules, creating a conducting channel through the atmosphere. Electrons accelerate through this channel at tremendous speeds, gaining enormous kinetic energy from the electric field. The energy heats the air to temperatures around 30,000 degrees, about 5 times hotter than the surface of the sun. The air expands explosively, creating the shock wave we hear as thunder, and the heated air glows, creating the flash we see as lightning. All of that energy, the light, the heat, the thunder, came from the electric field between the cloud and the ground. And that field's energy came from the atmospheric processes that separated the charges in the first place, ultimately traceable back to the heat energy from the sun that drives weather patterns. Once again, the chain is unbroken. The aurora borealis is another striking example. During solar storms, the sun hurls streams of charged particles toward Earth. These electrons encounter Earth's magnetic field and spiral along its field lines toward the poles. As they corkscrew downward through the upper atmosphere, they collide with nitrogen and oxygen molecules, transferring their kinetic energy to those molecules. The molecules release that energy as photons of green, red, and violet light. The shimmering curtains of color you see in the night sky above the Arctic are powered entirely by electrons that picked up their energy from the sun's magnetic and electric fields millions of miles away. The old cathode ray tube televisions that were common before flat screens worked on the same principle. Inside the tube, a heated metal filament released electrons through a process called thermionic emission. The heat gave the electrons enough energy to escape the metal. Then electric fields accelerated those electrons toward the front of the screen. The electrons hit a phosphor coating on the inside of the screen, and the impact made the phosphor glow. By steering the electron beam with magnetic fields, the television could paint an image on the screen, dot by dot, line by line. The energy that lit up each dot came from the kinetic energy of the electrons that struck the phosphor, and the electrons got that kinetic energy from the electric field inside the tube. And the field got its energy from the wall outlet. Every step is traceable. Now let's talk about potential energy, because potential energy and kinetic energy are deeply intertwined. You cannot truly understand one without the other. Potential energy is energy that depends on position. It is energy stored in the arrangement of objects within a field. A ball at the top of a hill has gravitational potential energy. It has not started moving yet. It has no kinetic energy, but it has the potential to gain kinetic energy if it rolls down the hill. The potential energy depends on the ball's position, specifically its height above the ground. The higher the ball, the more potential energy it has. When the ball rolls down the hill, its potential energy decreases and its kinetic energy increases. Energy is being converted from one form to the other. At the bottom of the hill, the ball has maximum kinetic energy and minimum potential energy. At the top, it had maximum potential energy and minimum kinetic energy. The total energy, kinetic plus potential, stays the same throughout the entire journey, assuming no friction. This is conservation of energy. The total does not change, it just shifts between forms. For electrons, the relevant field is not gravity but the electromagnetic field. An electron near a positively charged object has electric potential energy. The closer the electron is to the positive charge, the lower its potential energy, Because the electron is negatively charged and is attracted toward positive charges. If you pull the electron away from the positive charge, you increase its potential energy, just as lifting a ball increases its gravitational potential energy. You have to do work to pull the electron away, and that work is stored as potential energy. Now here is where it all connects. When you release the electron, it accelerates back toward the positive charge. As it moves closer, its potential energy decreases and its kinetic energy increases. The electron speeds up, gaining kinetic energy at the exact rate it loses potential energy. The total energy stays constant. This is conservation of energy in action. This is exactly what happens inside an atom, though with additional quantum rules we will explore later. The electron is attracted to the positively charged nucleus. It has electric potential energy because of its position relative to the nucleus. If the electron were to move closer to the nucleus, its potential energy would decrease and, in a simplified classical picture, its kinetic energy would increase. If it moved farther away, the reverse would happen. The total energy of the electron in the atom is the sum of its kinetic energy and its potential energy. And here is something important. For a bound electron, one that is trapped inside an atom, the total energy is negative. This sounds strange at first. How can energy be negative? The answer is that negative total energy simply means the electron is bound. It has less energy than it would if it were free and at rest, far from the atom. Think of it this way. We define zero total energy as the state where the electron is free, at rest, infinitely far from the atom, not interacting with anything. If the electron is bound inside an atom, it has less energy than that free state. It is in an energy well, a kind of valley that it cannot climb out of without receiving additional energy from somewhere. The negative total energy tells you how much energy you would need to add to free the electron. This quantity is called the binding energy. For the electron in the ground state of hydrogen, the binding energy is about 13.6 electron volts. That means you need to provide at least 13.6 electron volts of energy to rip the electron free from the hydrogen atom. If you provide less than that, the electron stays bound. It cannot leave. This interplay between kinetic and potential energy is fundamental to everything electrons do. In a simple electric circuit, electrons lose potential energy as they move through the wire from the negative terminal of a battery to the positive terminal. The potential energy they lose is converted into kinetic energy, which is then transferred to the atoms in the wire through collisions. The result is heat. In some devices, the energy is converted into light, sound, or mechanical motion instead. But the source of the energy is always the same. The electric potential energy established by the battery or generator. In a Van de Graaff generator, the kind you might have seen in science museums where people touch a metal sphere and their hair stands on end, charge is mechanically transported to the sphere, building up a large voltage. This creates a strong electric field around the sphere. If an electron happens to be near the sphere, the field does work on it, converting potential energy into kinetic energy. The electron accelerates away from the sphere, gaining speed. Early particle physics experiments used Van de Graaff generators as accelerators, pushing electrons and protons to energies of a few million electron volts. Not as powerful as modern accelerators, but powerful enough to explore the structure of atoms. Now let me address something that trips up a lot of people. The relationship between an electron's charge and its energy. These are not the same thing. Charge and energy are completely different properties. An electron's charge is a fixed, fundamental quantity. Every electron in the universe has exactly the same charge, about negative 1.6 times 10 to the negative 19 coulombs. That charge never changes. You cannot add charge to an electron or take charge away from it. An electron always has the same charge, whether it is moving or still, whether it is inside an atom or flying through a particle accelerator, whether it has a tiny amount of kinetic energy or an enormous amount. But the electron's energy can change dramatically. A slow electron and a fast electron have the same charge but vastly different kinetic energies. An electron bound tightly inside an atom and a free electron have the same charge but very different total energies. Charge determines how strongly the electron interacts with electric and magnetic fields. It determines the force the electron feels. But the energy the electron has depends on what those fields have done to it, on how much work has been transferred, on the electron's history of interactions. Charge is the handle by which fields grab the electron. Energy is the result of what happens after they grab it. Think of it like a sail on a boat. The sail determines how strongly the wind pushes the boat. A bigger sail catches more wind. But the sail is not the same thing as the boat's speed. The speed depends on how long the wind has been pushing, how heavy the boat is, whether there are currents or waves. The sail is a property that determines coupling to an external force. The speed is a consequence of that coupling over time. For an electron, charge is the sail and energy is the speed. They are connected, intimately connected, but they are not the same thing. This distinction is crucial because it prevents a common error. People sometimes think an electron has energy because it has charge. That is not correct. An electron has rest energy because it has mass. It gains additional kinetic energy when a field does work on it. The charge determines how much force the field exerts, but the energy itself comes from the work done by the field, not from the charge itself. If you placed a neutral particle with the same mass as an electron in an electric field, nothing would happen. The field would not push it because it has no charge. No work would be done. No kinetic energy would be gained. The charge is necessary for the interaction, but it is the interaction that transfers the energy. Let me also emphasize one more critical idea before we move on. Conservation of energy. In every single example we have discussed, energy was transferred, not created. The battery converts chemical energy to electric potential energy. The electric field converts potential energy to the kinetic energy of electrons. The electrons convert kinetic energy into heat through collisions with atoms. Lightning converts the electric potential energy between cloud and ground into heat, light, and sound. The particle accelerator converts electrical energy from the power grid into the kinetic energy of electrons. At no point does energy appear from nothing. At no point does energy vanish into nothing. It transforms, it flows, it shifts between forms. But the total amount of energy in a closed system never changes. This is one of the most fundamental principles in all of physics. It has been tested countless times in countless experiments, and it has never been violated. And here is why this matters for understanding the electron. The electron is not an energy source. It does not contain a hidden supply of energy that it can draw upon. When an electron does something that requires energy, when it emits light, when it does work on another particle, when it heats up a wire, that energy came from somewhere. It was transferred to the electron at some earlier point through an interaction with a field, a photon, or another particle. And when the electron releases energy, that energy goes somewhere. It does not disappear. It becomes a photon, or kinetic energy of another particle, or heat in a material. Everything balances. This is why physicists can track energy so precisely. When they measure what goes into a particle collision and what comes out, the books always balance. The total energy before the collision equals the total energy after the collision. If it did not, if energy could appear from nowhere or vanish into nothing, then physics itself would break down. The equations would not work. Predictions would fail. Technology based on those predictions would stop functioning. But the equations do work. Predictions are confirmed. Technology functions. Energy is conserved. So, to summarize what we have covered, beyond its rest energy, an electron can gain kinetic energy when an electric field does work on it. The electron accelerates, moves faster, and carries more energy. This is how circuits work, how particle accelerators work, how lightning works, how cathode ray tubes work. The energy comes from the field, not from inside the electron. The electron also has potential energy that depends on its position within a field. As the electron moves through the field, potential energy converts to kinetic energy and vice versa. The total energy is always conserved. Charge is not energy. Charge determines how strongly the electron couples to the field, but the energy itself comes from the work done by the field over time. And here is what ties it all together. The electron's rest energy came from its mass. Its kinetic energy came from fields doing work on it. Its potential energy comes from its position within those fields. Each contribution is distinct. Each has a clear physical origin, and each obeys conservation of energy without exception. The electron is not a battery. It is a participant in a vast network of energy transfers, receiving and giving energy as it interacts with the world around it. There is one more thing worth mentioning before we leave the classical world behind. Not all materials allow electrons to move freely. In a metal like copper, some electrons are loosely bound and can drift through the material when an electric field is applied. These are the electrons that carry current in a wire. But in other materials, the electrons are tightly bound to their atoms and cannot move easily. These materials are insulators. Glass, rubber, dry wood. An electric field pushes on the electrons in an insulator just as hard as it pushes on electrons in a metal, but the electrons cannot respond because they are locked in place by strong bonds to their atoms. Then there are semiconductors, materials like silicon that sit between conductors and insulators. In a semiconductor, electrons are bound, but not as tightly as in an insulator. With a small push, a modest amount of added energy from heat or light, or an applied voltage, some electrons can be freed to move. This is what makes semiconductors so useful. You can control whether they conduct or not by controlling the energy available to the electrons. And that controllability is the foundation of every transistor, every computer chip, every digital device in the modern world. The physics is still the same. An external source provides energy, the electron receives it. The electron moves, conservation holds. But we have not yet touched on the strangest part of the story. Because everything we have discussed so far, kinetic energy from motion, potential energy from position, these concepts work in the classical world. They apply to baseballs and planets and trucks on highways. But electrons are not classical objects. Inside an atom, electrons obey rules that have no equivalent in everyday life. Rules that dictate not just how much energy the electron can have, but which specific amounts of energy are allowed and which are absolutely forbidden. The rules of quantum mechanics. And those rules will change everything you think you understand about how energy works at the smaller scales. Everything we have discussed so far about kinetic energy and potential energy makes sense in the everyday world. A ball rolling down a hill converts potential energy into kinetic energy smoothly, continuously, passing through every speed between its initial speed and its final speed. A car accelerating on a highway gains kinetic energy gradually, moving through every possible value along the way. There are no gaps, no forbidden speeds, no jumps. The energy changes in a perfectly smooth, continuous flow, and for centuries, physicists assumed that the same smooth behavior applied at every scale, from planets to pebbles to molecules to atoms. They were wrong. When you zoom down to the scale of an electron inside an atom, the rules change. They do not bend, they do not soften, they change completely. And the change is so dramatic, so counterintuitive, so far from anything you have ever experienced in your daily life, that when physicists first discovered it in the early 20th century, many of them refused to believe it. But the evidence was undeniable. Electrons inside atoms do not behave like tiny planets orbiting a miniature sun. They do not circle the nucleus in smooth, predictable paths. They do not have any energy they please. Instead, electrons inside atoms are restricted to specific, discrete energy values. Certain amounts of energy are allowed. Everything in between is forbidden. The electron can have this energy or that energy, but nothing in between. It is as if you were climbing a staircase where your feet could land on any step, but you could never stand between steps. The space between steps simply doesn't exist for you. This is quantization, and it is one of the most revolutionary ideas in the history of science. To understand why electrons in atoms can only carry certain energies, we need to confront something uncomfortable. The electron is not what you think it is. You probably picture an electron as a tiny ball, a little sphere of negative charge whizzing around the nucleus like a planet around a star. This picture is deeply embedded in popular culture. You see it in textbook diagrams, in company logos, in science fiction films. Neat little circles with a dot at the center and a few elliptical paths drawn around it. It looks clean and simple, and it is completely wrong. An electron is not a little ball. An electron behaves as a wave, not a water wave, not a sound wave, a quantum mechanical wave, a wave of probability. This was one of the most shocking discoveries in the history of physics. Proposed by the French physicist Louis du Broglie in 1924. Du Broglie suggested that every particle, not just light, has a wave nature. A moving electron has an associated wavelength, just as a beam of light does. The faster the electron moves, the shorter its wavelength. The slower it moves, the longer its wavelength. For large objects like baseballs and cars, the wavelength is so incredibly tiny that it has no measurable effect. But for something as small and light as an electron, the wavelength becomes significant. It becomes comparable to the size of an atom itself. And when that happens, the wave nature dominates. The electron stops behaving like a ball and starts behaving like a vibrating string. This is where the restriction on energy comes from. Think about a guitar string. A guitar string is fixed at both ends. When you pluck it, it vibrates. But it cannot vibrate in just any pattern. Because the string is fixed at both ends, only certain vibration patterns are possible. The simplest pattern is one big arc, one smooth curve from one end to the other. This is the fundamental mode. The next allow pattern has two arcs, one going up and one going down with a node, a point of zero vibration, in the middle. then 3 arcs with 2 nodes, then 4 arcs with 3 nodes, and so on. Each pattern has a specific frequency and a specific wavelength. You cannot have a pattern with 1.5 arcs. The string would not satisfy the boundary conditions, it would not be fixed at both ends. The half-arc vibration simply does not work. Only whole number patterns are allowed. An electron inside an atom faces a similar constraint, but in 3 dimensions rather than 1. The electron's wave must fit around the nucleus in a way that is self-consistent. Imagine bending the guitar string into a circle. Now the wave has to connect back to itself. If you go around the circle, the wave has to match up where it started. If it does not, the wave destructively interferes with itself and cancels out. It ceases to exist. Only certain wavelengths fit perfectly around the circle so that the wave reconnects with itself after going all the way around. 1 complete wavelength fits, 2 complete wavelengths fit, 3 fit, but 1.5 wavelengths do not. The wave would be out of phase when it came back around, and it would destroy itself through destructive interference. This is the physical origin of quantized energy levels. Each allowed wave pattern corresponds to a specific energy. The electron can exist in the wave pattern with 1 wavelength fitting around the nucleus, or 2, or 3, or any whole number. Each of these patterns has a definite, calculable energy, but the electron cannot exist in a state between these patterns. There is no stable wave pattern corresponding to 1.5 wavelengths. So, there is no energy state between the first and second allowed levels. The energies are quantized. They come in specific discrete values with nothing in between. This idea was first formalized by the Danish physicist Niels Bohr in 1913, though his model was simpler and less complete than the full quantum mechanical treatment that followed. Bohr proposed that electrons in atoms could only occupy certain orbits, each with a specific energy. He did not yet understand the wave nature of the electron. That understanding came later with du Broglie and with Erwin Schrödinger, the Austrian physicist who in 1926 wrote down the equation that governs the behavior of quantum waves. The Schrödinger equation is to quantum mechanics what Newton's laws are to classical mechanics. It tells you how a quantum wave evolves over time, what shapes it can take, and what energies are allowed. When you solve the Schrödinger equation for an electron in a hydrogen atom, you get a set of allowed energy levels. These levels are not inputs to the equation, they are outputs. They emerge naturally from the mathematics of waves confined in a potential well, just as the allowed vibration patterns of a guitar string emerge from the mathematics of waves on a fixed string. The physics dictates the allowed energies. Nature decides. Let me walk you through the energy levels of hydrogen because hydrogen is the simplest atom that exists. 1 proton in the nucleus, 1 electron around it, nothing else. And even the simplest of atoms produces a set of energy levels that reveals the deep structure of quantum mechanics. The lowest energy level, called the ground state, corresponds to the quantum number n equals 1. In this state, the electron has a total energy of negative 13.6 electron volts. Remember, the negative sign means the electron is bound. It has less energy than a free electron at rest. You would need to provide 13.6 electron volts to tear the electron completely free from the hydrogen atom. This is the most tightly bound state. The electron is as close to the nucleus as quantum mechanics allows. It cannot fall any lower. There is no energy level below n equals 1. The ground state is the bottom of the staircase. But here is something remarkable about that bottom step. The electron sitting in the ground state is not sitting still. It still possesses kinetic energy even though it cannot possibly drop any lower. This seems strange. If the ground state is the lowest energy level, why does the electron have any kinetic energy at all? The answer comes from a principle formulated by the German physicist Werner Heisenberg in 1927. The uncertainty principle. Heisenberg showed that you cannot simultaneously know both the exact position and the exact momentum of a particle with perfect precision. The more precisely you pin down where the electron is, the less precisely you can know how fast it is moving. And the reverse is equally true. This is not a limitation of our instruments. It is a fundamental property of nature itself. Inside a hydrogen atom, the electron is confined to a very small region of space near the nucleus. Because the electron's position is constrained, the uncertainty in its momentum must be large. A large uncertainty in momentum means the electron must have a significant amount of kinetic energy. It cannot be motionless. A perfectly still electron would have a precisely known momentum of 0. And that would violate the uncertainty principle given how tightly confined it is. So, the ground state is a compromise. The electron settles into the lowest energy arrangement that satisfies both the wave equation and the uncertainty principle simultaneously. It still has kinetic energy, but it has the minimum possible kinetic energy consistent with being confined near the nucleus. This residual motion energy is sometimes called zero-point energy. It is the energy of confinement itself, the price the universe pays for keeping the electron localized. And it cannot be extracted or removed, because there is no lower state to fall into. The next allowed level is n equals 2. In this state, the electron's total energy is negative 3.4 electron volts. Notice the jump from negative 13.6 to negative 3.4. That is a difference of 10.2 electron volts. The electron went from the first step to the second step, and the gap between those steps is 10.2 electron volts. There is no energy state at negative 10 electron volts, or negative 8, or negative 5. Nothing exists between the ground state and the first excited state. The electron is either at n equals 1 with negative 13.6 electron volts, or at n equals 2 with negative 3.4 electron volts. There is no in-between. The third level, n equals 3, has an energy of negative 1.51 electron volts. The fourth level is negative 0.85 electron volts. As you go higher, the levels get closer together, crowding towards 0. At n equals 7, the energy is only negative 0.28 electron volts. The electron is barely bound. A tiny additional push would free it from the atom entirely. These energy levels follow a precise mathematical pattern. The energy of each level is proportional to 1 over n squared, where n is the quantum number. This pattern is not arbitrary. It comes directly from solving the Schrödinger equation for the hydrogen atom. The equation encodes the physics of the electromagnetic attraction between the proton and the electron, combined with the wave nature of the electron, and it produces this specific set of allowed energies as its solution. Now here is the key question. How does an electron move between these levels? How does it go from n equals 1 to n equals 2, or from n equals 3 to n equals 1? The answer is photons. A photon is a particle of light. It carries a specific amount of energy determined by its frequency. High-frequency photons like ultraviolet light and X-rays carry a lot of energy. Low-frequency photons like infrared light and radio waves carry very little, and the energy of a photon is exactly determined by its frequency. There is a direct, precise relationship between the two, first described by the German physicist Max Planck at the beginning of the 20th century. When an electron in an atom absorbs a photon, the electron gains the photon's energy, but it cannot gain just any amount. It can only gain amounts that correspond to the gap between two allowed energy levels. If the electron is in the ground state of hydrogen at negative 13.6 electron volts, it can absorb a photon with exactly 10.2 electron volts of energy. That specific amount of energy lifts the electron from n equals 1 to n equals 2. The photon vanishes. Its energy has been transferred to the electron, which is now in the higher energy state. But what if a photon with 9 electron volts arrives? 9 electron volts does not match the gap between any two energy levels in hydrogen. There is no state the electron can jump to by absorbing 9 electron volts. So, the electron ignores the photon. It passes right through the atom without being absorbed. The atom is transparent to that particular photon. This is remarkably selective. The atom does not absorb photons of arbitrary energy. It only absorbs photons whose energy exactly matches the gap between two allowed levels. Everything else passes through. The reverse process is equally precise. When an electron drops from a higher energy level to a lower one, it emits a photon. The energy of that photon is exactly equal to the energy difference between the two levels. An electron dropping from n equals 2 to n equals 1 in hydrogen emits a photon with exactly 10.2 electron volts of energy. That photon has a specific frequency and a specific wavelength. It is an ultraviolet photon. An electron dropping from n equals 3 to n equals 2 emits a photon with about 1.89 electron volts. That is a red photon with a wavelength of about 656 nanometers. This specific red line is called the H-alpha line, and it is one of the most important spectral lines in all of astronomy. It is the light that makes many nebulae glow red. Every time you see a photograph of a glowing red nebula in space, you are seeing the H-alpha line. You are seeing the specific photon that hydrogen atoms emit when their electrons drop from the third energy level to the second. One particular quantum jump produces one particular color of light, visible across the entire universe, and this brings us to one of the most powerful pieces of evidence for quantized energy levels: spectral lines. When you heat hydrogen gas and look at the light it produces through a prism, you do not see a smooth rainbow of all colors. Instead, you see a series of sharp, bright lines at very specific wavelengths: red, blue-green, violet, and a few others in the ultraviolet. Nothing in between, just sharp lines separated by darkness. These lines correspond precisely to the energy differences between the allowed levels in the hydrogen atom. The red line at 656 nanometers is the electron dropping from n equals 3 to n equals 2. The blue-green line at 486 nanometers is the drop from n equals 4 to n equals 2. The violet line at 434 nanometers is the drop from n equals 5 to n equals 2. This pattern was actually observed long before anyone understood why it existed. In the 1860s, physicists noticed that hydrogen produced these specific lines and nothing else. They could measure the wavelengths with great precision. They could catalog them. But they had no explanation for why hydrogen produced these particular wavelengths, and no others. It was a mystery that lasted for decades. It was not until Niels Bohr's model in 1913, and later the full quantum mechanical treatment, that the explanation became clear. The lines exist because the energy levels are quantized. The electron can only transition between specific allowed states. Each transition produces a photon with a specific energy, which corresponds to a specific wavelength. The sharp spectral lines are direct, visible, undeniable evidence that energy inside atoms is quantized, and every element has its own unique set of spectral lines. Helium produces different lines than hydrogen, sodium produces different lines than helium, iron produces different lines than sodium. Each element has a different number of protons in its nucleus, which changes the electric potential the electron sits in, which changes the solution to the Schrödinger equation, which changes the allowed energy levels, which changes the spectral lines. The spectral lines of an element are like a fingerprint, absolutely unique, and astronomers use these fingerprints to determine what distant stars and galaxies are made of. When they see the characteristic lines of hydrogen in the light from a distant star, they know that star contains hydrogen. When they see iron lines, they know there is iron. All of this works because energy levels in atoms are quantized, producing spectral lines at precise wavelengths that serve as unmistakable chemical signatures. And these quantum jumps do not only light up distant nebulae and reveal the composition of stars, they power technologies you use every single day. A laser works by exploiting quantized energy levels in a very precise way. Inside a laser, atoms or molecules are pumped into excited states using an external energy source, an electric current, a flash lamp, or another laser. When one of these excited atoms emits a photon, that photon can stimulate a neighboring excited atom to emit an identical photon at the same frequency, in the same direction, perfectly in phase. That second photon stimulates a third. The third stimulates a fourth. The result is a cascade of perfectly synchronized photons, all with the same wavelength, all marching together. That is laser light. Coherent, intense, and precise. None of it would work if energy levels were not quantized. If electrons could have any energy they pleased, there would be no well-defined gap to produce photons of a single precise wavelength. The laser would be impossible. LEDs work on a similar principle, but in a semiconductor rather than a gas. Electrons in the semiconductor drop from a higher energy band to a lower one, and the energy difference is released as a photon. The specific gap between the bands determines the color of the light. Change the semiconductor material, and you change the gap, and you change the color. Red, green, blue, white, each color corresponds to a specific quantized energy difference in a specific material. Fluorescent lights work by a related mechanism. An electric current excites mercury atoms inside the tube. The mercury atoms emit ultraviolet photons when their electrons drop between levels. Those ultraviolet photons strike a phosphor coating on the inside of the glass, which absorbs them and re-emits visible light at lower energies. Every stage of that process is a quantized transition, an electron jumping between allowed levels and producing a photon with a precise energy. Now, there is a deeper point here that most popular explanations miss entirely. When we talk about the electron's energy inside an atom, we need to be very careful about what we mean, because in a subtle but important sense, the energy does not belong to the electron alone. It belongs to the system. Think about it. The electron in a hydrogen atom has kinetic energy because it is in a dynamic quantum state. It has potential energy because of its electromagnetic interaction with the proton. But that potential energy does not belong to the electron alone. It belongs to the system of the electron and the proton together. The potential energy is a property of their arrangement, their separation, their mutual interaction. If you remove the proton, the potential energy would not stay behind attached to the electron. It would vanish because there would no longer be two charges interacting. The potential energy is a property of the relationship between the charges, not a property of either charge individually. This is why physicists talk about the energy levels of the hydrogen atom, not the energy levels of the electron alone. When we say the ground state of hydrogen has an energy of negative 13.6 electron volts, we are describing the energy of the entire system. Electron plus proton plus their electromagnetic interaction. The electron contributes kinetic energy. The proton contributes a tiny amount of kinetic energy. The electromagnetic field between them contributes potential energy. The total, when you add it all up, is negative 13.6 electron volts. The individual contributions cannot be cleanly separated in a simple way because they are all entangled through the quantum state of the system. This matters because it prevents a common mistake. People sometimes ask how much energy the electron has inside a hydrogen atom, as if the electron carries a specific, well-defined amount of energy that belongs entirely to it. But inside a bound system, energy is shared. The total energy of the system is well-defined. The individual contributions are intertwined. When we say the electron dropped from n equals 3 to n equals 2, what we really mean is that the hydrogen atom as a complete system transitioned from one energy state to another. The electron's wave function changed. The potential energy between the electron and proton changed. The kinetic energy changed. And the difference in total system energy was carried away by the emitted photon. Everything happened together as a coordinated change in the whole system. This idea extends beyond hydrogen. In any atom, in any molecule, in any solid material, the energy states are properties of the entire system, not of individual particles in isolation. When you see a neon sign glowing orange-red, that color comes from specific transitions in neon atoms. But those transitions involve the entire neon atom, all 10 electrons interacting with the 10 protons in the nucleus and with each other. The energy levels of neon are determined by the collective quantum state of the whole system. Remove one electron and the energy levels change. Add an electron and they change again. The levels are not painted on individual electrons like price tags. They emerge from the collective behavior of the entire atomic system. This becomes even more dramatic in heavier atoms. In hydrogen, there is only one electron interacting with one proton. The energy levels are clean and relatively simple. But in an atom like iron, with 26 electrons and 26 protons in the nucleus, the situation is vastly more complex. Each electron interacts not only with the nucleus, but with all the other electrons. These electron-electron interactions push and pull on the energy levels, splitting them, shifting them, rearranging them into patterns that look nothing like hydrogen's simple staircase. The energy landscape of a heavy atom is shaped by every particle in the system simultaneously. This is why iron has a completely different set of spectral lines than hydrogen or helium. It is not just that the nucleus is heavier. It is that 26 electrons are all jostling within the same potential well, each one affecting the allowed states of every other. The energy levels are collective. They belong to the system as a whole, and they cannot be understood by looking at any single electron in isolation. This reinforces the point. Energy inside an atom is a property of the entire system, not a label attached to one particle. Let me now return to binding energy and explain it more carefully because it reveals something profound about how energy works in quantum systems. We said that the ground state of hydrogen has an energy of negative 13.6 electron volts. That negative sign tells us the electron is bound. But what does that really mean? Imagine you have a free electron and a free proton, both at rest, very far apart from each other. They are not interacting. They are just sitting in empty space, doing nothing. In this configuration, the total energy of the system is just the rest energy of the electron plus the rest energy of the proton. No kinetic energy because both particles are at rest. No potential energy because they are too far apart to interact significantly. We define this as zero total energy, zero beyond the rest energies. Now, let the proton's electric field reach the electron. The electron feels the attraction and begins to fall toward the proton. As it falls, it gains kinetic energy, just as a ball gains kinetic energy falling toward Earth. At the same time, it loses potential energy. But if nothing else happens, the electron would just fly past the proton and head out the other side, like a comet swinging past the sun. To actually become bound, to settle into a stable energy state, the system has to lose energy. It has to get rid of some of the energy that the electron gained during its fall. How does it do this? By emitting a photon. As the electron settles into the ground state, the atom emits a photon that carries away exactly 13.6 electron volts. That photon flies off into space, taking energy with it. The system, the hydrogen atom, now has less total energy than it started with. It started with zero beyond rest energies, and it now has negative 13.6 electron volts. The difference went into the photon. This is binding energy. It is the energy the system released when the electron became bound. And it is also the energy you would need to supply to reverse the process, to break the electron free. If you send a photon with 13.6 electron volts of energy into the hydrogen atom, the atom absorbs it, and the electron gains enough energy to escape. The atom is ionized. The electron is free. The system is back to zero total energy. This is why a bound electron has less total energy than a free electron. It gave up energy when it became bound. It lost energy to become part of the atom, and it would need to receive that energy back to become free again. This is not intuitive. In everyday life, we associate being trapped with having too little energy to escape, which is correct. But we do not usually think about the fact that the act of becoming trapped involved releasing energy. When a satellite is captured into orbit around a planet, the capture requires the satellite to lose energy, often through atmospheric drag or a gravitational interaction with a third body. The energy it loses is what keeps it trapped. Without losing energy, the satellite would fly past the planet and continue on its way. The same principle applies to the electron being captured into an atom. The electron had to lose energy, emitted as a photon, to become bound. And now you can see how all the pieces connect. The electron has rest energy from its mass, it has kinetic energy from its motion, it has potential energy from its position relative to the nucleus, and the quantum wave nature of the electron restricts which combinations of kinetic and potential energy are allowed. Only specific total energies are permitted. The electron exists in one of these allowed states, or it does not exist in the atom at all. When it transitions between states, it absorbs or emits a photon carrying exactly the right amount of energy. and the total energy of the complete system is always conserved. There's one more thing I want to address before we move on, because it comes up whenever people learn about quantized energy levels. People ask, what happens between the levels? When an electron jumps from n equals 2 to n equals 1, does it pass through the intermediate energies? Does it smoothly slide from 3.4 electron volts to 13.6 electron volts? The answer, as far as quantum mechanics tells us, is no. The electron does not pass through intermediate states. It transitions instantaneously from one allowed state to another. One moment it is in the n equals 2 state with the corresponding wave function and energy. The next moment it is in the n equals 1 state with a completely different wave function and energy, and a photon has appeared, carrying the energy difference. This idea was deeply troubling to physicists when it was first proposed. Even Niels Bohr, who suggested quantized orbits, struggled with the concept. Werner Heisenberg, another founding figure of quantum mechanics, built an entire formulation of the theory in 1925, based on the idea that physics should only describe observable quantities, like the energies of the allowed states and the frequencies of the emitted photons, rather than trying to describe what happens between observations. In his framework, the question of what the electron does between levels is not just unanswered, it is meaningless. There is no trajectory between levels. There is no path. There is only the initial state, the final state, and the photon that carries the energy difference. You might find this unsatisfying. You might want to know what really happens during the transition. But quantum mechanics, as currently understood, does not provide a detailed blow-by-blow account of the jump. It provides the probabilities of transitions. It tells you which transitions are more likely and which are less likely. It tells you the rate at which transitions happen, but it does not describe a smooth path from one state to another. The transition is fundamentally discontinuous. This is one of the deepest and most unsettling features of quantum mechanics, and after a century of testing, it remains one of its most solidly confirmed predictions. So, let us step back and see what we have built. Inside an atom, the electron's wave nature creates standing wave patterns that restrict the allowed energies to discrete values. The electron can only possess energies that correspond to these standing wave solutions. Everything in between is forbidden. When the electron transitions from one allowed state to another, it absorbs or emits a photon whose energy exactly matches the gap between the states. The spectral lines we observe in starlight are direct evidence of these quantized states, fingerprints of atoms written in light, and the energy of these states belongs to the atom as a complete system, not to the electron alone. The electron, the nucleus, and the electromagnetic field between them all contribute to the total energy of each quantum state. The staircase of allowed energies is not a limitation imposed from outside. It emerges from the physics itself, from the wave nature of the electron and the shape of the potential well created by the nucleus. It is as fundamental as the structure of the atom, and it governs every interaction that atoms have with light, which means it governs the colors of everything you see, the chemical reactions that power your body, the operation of lasers, the glow of neon signs, the light from stars, and the cosmic background radiation left over from the birth of the universe. But energy levels and photon absorption are not the whole story. Electrons do not only live inside atoms, they can be free. They can collide with other particles. They can move at speeds close to the speed of light, where the familiar rules of classical physics break down once more, and Einstein's special relativity takes over. And when you combine quantum mechanics with special relativity, the picture of the electron's energy becomes both more complete and more strange than anything we have encountered so far. That is where we are going next. We have built the story piece by piece. Rest energy from mass, kinetic energy from fields doing work, potential energy from position within a field, quantized energy states from the wave nature of the electron confined inside an atom. Each contribution is physically distinct, each has a clear origin, and each respects a rule so fundamental that no experiment has ever found a single exception. Conservation of energy. Energy is never created from nothing. Energy never vanishes into nothing. It flows, it transforms, it moves between systems, but the total amount in a closed system always stays the same. Now it's time to bring all of these pieces together and see the full picture. Because in the real universe, electrons do not live in textbooks where one concept is neatly separated from the next. They exist in a world where photons arrive without warning, where collisions happen at nearly the speed of light, where relativity warps the relationship between energy and motion, and where the boundaries between different forms of energy blur and shift depending on how you look at the system. This ties everything together and reveals the complete answer to the question we start with. Where does an electron really get its energy from? Let's start with photons, because photons are the primary currency of energy exchange in the quantum world. We talked about photons in the context of atoms, where an electron absorbs a photon and jumps to a higher energy level, or emits a photon and drops to a lower one. But photon interactions are far more varied and far more interesting than just those atomic transitions. Photons can interact with electrons in many different ways, and each type of interaction tells us something important about how energy moves at the smallest scales. One of the most fundamental interactions is called Compton scattering. In 1923, the American physicist Arthur Compton fired X-ray photons at a block of graphite and measured what came out the other side. He found that the X-rays that bounced off the material had a longer wavelength than the X-rays that went in. Longer wavelength means lower frequency. Lower frequency means less energy. The photons had lost energy. Where did that energy go? It went into the electrons. The photons collided with electrons in the graphite and transferred some of their energy to those electrons, knocking them loose from their atoms and sending them flying. The photon lost energy and the electron gained energy. The total energy before the collision equaled the total energy after. Nothing was created. Nothing was lost. Energy was simply transferred from the photon to the electron. Compton scattering was a pivotal experiment because it proved that photons behave like particles in collisions. They carry energy and momentum, and they can transfer both to electrons through direct impact, much as a billiard ball transfers energy and momentum to another billiard ball when they collide. But unlike billiard balls, the photon can change its wavelength in the process. A photon that gives up energy does not slow down. Photons always travel at the speed of light. Instead, it shifts to a longer wavelength and lower frequency. The energy of a photon is entirely determined by its frequency. Change the frequency and you change the energy. This is fundamentally different from how ordinary objects behave, and it is a direct consequence of the quantum nature of light. The reverse process also occurs. A high-energy electron can collide with a low-energy photon, and boosts the photon to much higher energy. This is called inverse Compton scattering, and it happens throughout the universe. Near the supermassive black hole at the center of our galaxy, Sagittarius E star, electrons spiraling in intense magnetic fields can scatter photons up to X-ray and even gamma-ray energies. The electron loses energy in the process, and the photon gains it. Once again, the total is conserved. The electron gave up kinetic energy, and the photon carried that energy away. Another important photon process is the photoelectric effect. This is the phenomenon that Albert Einstein explained in 1905, the same year he published his famous mass-energy equivalence. When a photon with sufficient energy strikes a metal surface, it can eject an electron from the metal entirely. The photon is absorbed, and its energy is transferred to the electron. Part of that energy goes into overcoming the binding energy that holds the electron in the metal. The remainder becomes the kinetic energy of the ejected electron. If the photon does not have enough energy to overcome the binding energy, the electron stays put. The photon is either reflected or it passes through. This all-or-nothing behavior was one of the key pieces of evidence that light is quantized, that it comes in discrete packets of energy rather than continuous waves. The photoelectric effect is not just a laboratory curiosity. It demonstrated a principle that underlies much of modern technology. A closely related process, the photovoltaic effect, is what powers solar panels. When sunlight hits a photovoltaic cell, photons transfers their energy to electrons inside the semiconductor material, promoting them from a lower energy band to a higher one. Those energized electrons flow through a circuit, and that flow of electrons is electricity. The energy that powers the circuit came from the photons, which came from the sun, which generated those photons through nuclear fusion in its core. The chain stretches from nuclear physics in the heart of a star to the electricity powering a device in your hand. Every link in that chain is an energy transfer. Photon to electron, electron through circuit, circuit to device. Nothing is created from nothing at any point. Now let's talk about collisions between particles, because collisions are another major way electrons gain and lose energy. In a particle accelerator, physicists smash particles together at enormous energies. When high-energy electrons collide with other particles, the kinetic energy of the collision can be converted into entirely new particles. This is mass energy equivalence working in reverse. Instead of mass converting into energy, energy converts into mass. If two electrons collide with enough kinetic energy, the collision can produce additional particles. An electron-positron pair, for example. The kinetic energy of the original electrons is converted into the rest mass of the new particles. The new particles literally materialize from the energy of the collision. Before the collision, that energy existed as kinetic energy of the two incoming electrons. After the collision, some of that energy exists as the mass of the new particles. The total energy, kinetic energy, plus rest energy of all particles is exactly the same before and after. Nothing appeared from nothing. The new particles were paid for by the kinetic energy of the originals. This process happens in reverse too. When an electron meets a positron, they annihilate. Both particles vanish. Their combined rest energy, about 1.022 mega electron volts, is converted entirely into photons. If the electron and positron were also moving, their kinetic energy is added to the photon energies as well. The total energy of the photons equals the total energy of the original particles. Perfect conservation, perfect accounting. Every fraction of an electron volt is accounted for. Electrons can also lose energy through a process called Bremsstrahlung, a German word meaning breaking radiation. When a fast-moving electron passes close to an atomic nucleus, the electric field of the nucleus deflects the electron, changing its direction. This change in direction is an acceleration, and accelerating charged particles emit electromagnetic radiation. The electron slows down and emits a photon. The energy of the photon equals the kinetic energy the electron lost. Bremsstrahlung is one of the main ways that X-rays are produced in medical imaging. Inside an X-ray tube, electrons are accelerated to high speeds and then slammed into a metal target. As they decelerate in the electric fields of the target's atoms, they emit X-ray photons. The X-ray energy came from the kinetic energy of the electrons, and the electrons' kinetic energy came from the electric field that accelerated them. And that field's energy came from the electrical power supply. The chain is always traceable. A related process is synchrotron radiation. When an electron moves in a circle, as it does when a magnetic field bends its path, it is constantly accelerating because the direction of its motion is constantly changing. An accelerating charge emits radiation. So, electrons spiraling in magnetic fields constantly lose energy by emitting photons. This is how many astronomical objects produce light. Pulsars, neutron stars that spin rapidly and have intense magnetic fields, produce beams of synchrotron radiation as electrons spiral along their magnetic field lines. Active galaxies and quasars produce enormous jets of synchrotron radiation from electrons spiraling in the magnetic fields near their central black holes. The energy radiated comes from the kinetic energy of the electrons, which in turn came from the gravitational and electromagnetic fields that accelerated those electrons in the first place. Some of the most energetic electrons in the universe get their energy from supernova shockwaves. When a massive star explodes, the expanding blast wave plows through surrounding gas. Electrons caught near the shock front bounce back and forth across it, deflected by magnetic fields on either side. Each crossing gives the electron a small energy boost. After thousands of crossings, the electron reaches extraordinary energies. Physicists call this process Fermi acceleration. Even here, the energy is traceable. It came from the kinetic energy of the expanding shock wave, which came from the gravitational collapse that triggered the explosion. Now we need to address something we have been building toward throughout this entire journey: relativistic energy. Because when electrons move at speeds close to the speed of light, the simple formula for kinetic energy, 1/2 times mass times speed squared, no longer works. It gives the wrong answer. At high speeds, you need Einstein's special relativity to correctly calculate the electron's energy. And the relativistic formula reveals something profound about the relationship between energy, mass, and motion. There is an older way of explaining this that you might have encountered. Some textbooks used to talk about relativistic mass, the idea that an object's mass increases as it approaches the speed of light. In this picture, the faster you go, the heavier you become. And that is why you can never reach the speed of light, because your mass would become infinite, and it would require infinite energy to accelerate you further. This explanation is not exactly wrong, but modern physicists consider it misleading. It suggests that the object physically changes, that it becomes more massive in some intrinsic sense. It does not. The electron's rest mass is always 0.511 mega electron volts. That never changes, no matter how fast the electron moves. What changes is the total energy. The correct way to think about relativistic energy is through the energy-momentum relation. This is one of the most important equations in modern physics. And it goes like this: E squared equals pc squared plus mc squared squared. Here, E is the total energy of the particle. The quantity p is its momentum. The letter c is the speed of light, and m is the rest mass, the mass the particle has when it is sitting still. This equation tells you the total energy of a particle given its momentum and its rest mass. Let's unpack what this equation means. When the electron is sitting still, its momentum is 0. The equation simplifies to E squared equals mc squared squared, which means E equals mc squared. That is just the rest energy we talked about at the very beginning, the famous equation, the energy of simply existing. When the electron is moving, it has momentum, and the pc squared term adds to the total energy. The faster the electron moves, the larger its momentum, and the larger its total energy becomes. At speeds much lower than the speed of light, this equation gives answers that match the familiar 1/2 mass times speed squared formula. But at speeds approaching the speed of light, the two formulas diverge dramatically. The relativistic equation gives the correct answer. The classical formula does not. Here is what happens as the electron approaches the speed of light. At 90% of the speed of light, the electron's total energy is about 1.17 mega electron volts, roughly twice its rest energy. The extra energy beyond the rest energy is kinetic energy. At 99% of the speed of light, the total energy jumps to about 3.6 mega electron volts, roughly 7 times the rest energy. At 99.9%, it is about 11.4 mega electron volts. At 99.99%, about 36 mega electron volts. The energy keeps climbing, faster and faster. Each tiny increment of speed requires enormously more energy. Going from 99.9% to 99.99% of the speed of light requires far more additional energy than going from 0 to 90%. The relationship between speed and energy becomes wildly nonlinear as you approach the speed of light. This is why you can never actually reach the speed of light with a particle that has mass. To reach exactly the speed of light, the total energy would have to become infinite. No finite amount of energy can get you there. This is not an engineering limitation that could be overcome with better technology. It is a mathematical fact built into the structure of space-time. In the most powerful particle accelerators, electrons are routinely pushed to 99.9999% of the speed of light and beyond. The energy of these electrons is measured in giga-electron volts, billions of electron volts. Remember, the rest energy of an electron is only 0.511 mega electron volts. An electron at 100 giga electron volts has roughly 200,000 times more energy than its rest energy. Almost all of that energy is kinetic energy, pumped into the electron by the electromagnetic fields of the accelerator. The electron's rest mass has not changed at all. It is still the same electron it always was. But the total energy it carries has been amplified by a factor of 200,000 through the work done by the accelerating fields. The energy-momentum relation also applies to massless particles like photons. For a photon, the rest mass is 0. The equation simplifies to E equals P times C. The photon's energy is entirely determined by its momentum. It has no rest energy because it has no rest mass. This is why photons always travel at the speed of light. They have no mass to resist acceleration. They cannot slow down or speed up. They exist only at light speed, carrying energy and momentum in proportions determined by their frequency. Now, let me bring everything together. Because if you have followed this journey from the beginning, you now have all the pieces you need to answer the question we started with. Where does an electron really get its energy from? The answer is that the electron's energy comes from several physically distinct sources, and the amount of energy you measure depends entirely on what the electron is doing and what system it is part of. The first source is rest energy. The electron has mass. That mass is approximately 9.109 times 10 to the negative 31 kilograms. Through the relationship E equals mc squared, that mass corresponds to a rest energy of about 0.511 mega electron volts. This mass exists because the electron interacts with the Higgs field, which fills all of space with a non-zero value. The Higgs field gives the electron the property of mass, but it is not continuously supplying energy. The rest energy is a permanent feature of the electron, inseparable from its existence. You cannot reduce it without destroying the electron. The second source is kinetic energy. When an electric field does work on the electron accelerates and gains kinetic energy. This is how circuits work, how particle accelerators work, how lightning works. The kinetic energy comes from the field, not from inside the electron. The electron is the recipient, not the source. At low speeds, the kinetic energy follows the familiar classical formula. At speeds approaching the speed of light, the relativistic energy-momentum relation takes over, and the kinetic energy grows without bound as the electron approaches, but never reaches light speed. The third source is potential energy. An electron positioned within an electric field has potential energy that depends on its location relative to other charges. When the electron moves through the field, potential energy converts to kinetic energy and vice versa. The potential energy is not a property of the electron alone. It is a property of the system, of the arrangement of charges and their mutual interactions. Remove the other charges, and the potential energy vanishes. The fourth source is quantized energy from the electron's state inside a bound system like an atom. Inside an atom, the wave nature of the electron restricts the allowed energies to discrete values. The electron can occupy the ground state or an excited state, but nothing in between. When the electron transitions between states, it absorbs or emits a photon whose energy exactly matches the gap between the levels. These quantized energies belong to the atom as a complete system, not to the electron alone. They emerge from the interplay of the electron's wave nature and the electromagnetic potential created by the nucleus. Each of these sources is real. Each is measurable. Each is physically distinct from the others, and none of them involves energy appearing from nowhere or being generated by the electron itself. The electron does not contain energy the way a battery contains charge. It participates in a web of interactions, and its energy at any given moment is determined by those interactions. And through all of this, conservation of energy holds without exception. When an electron in an atom absorbs a photon and jumps to a higher level, the photon disappears and its energy is added to the system. When the electron drops back down, it emits a photon that carries away exactly the right amount of energy. When an electron is accelerated in a particle accelerator, The energy it gains comes from the electromagnetic fields of the machine, which draw power from the electrical grid. When an electron and positron annihilate, their combined rest energy becomes the energy of the resulting photons. At every step, the total energy of the complete system stays the same. Nothing is created. Nothing is destroyed. Everything is transferred. This principle, conservation of energy, is not just a rule that physicists chose to follow because it is convenient. It is a consequence of something deep about the structure of the universe. In 1918, the German mathematician Emmy Noether proved a theorem that connects conservation laws to symmetries of nature. Noether's theorem says that if the laws of physics do not change over time, if an experiment done today gives the same result as the same experiment done tomorrow, then energy must be conserved. The conservation of energy is a direct consequence of the fact that the universe's laws are constant in time. As long as the laws of physics remain the same from moment to moment, energy cannot be created or destroyed. This is one of the most beautiful results in all of theoretical physics. A deep symmetry of nature gives rise to a conservation law that governs everything from the tiniest electron to the largest galaxy cluster. So, what is the final answer? The electron's energy is not one thing. It is several things, depending on what you are measuring. If you are measuring the energy of a stationary electron in empty space, you are measuring its rest energy, a consequence of its mass and its interaction with the Higgs field. If you are measuring the energy of an electron flying through a particle accelerator, you are measuring its rest energy plus the kinetic energy pumped into it by the accelerating fields. If you are measuring the energy of an electron bound inside a hydrogen atom, you are measuring the total energy of the atomic system, a combination of kinetic energy, potential energy, and the quantum constraints imposed by the electron's wave nature. If you are measuring the energy of a photon emitted by a transitioning electron, you are measuring the energy difference between two quantized states of the atom. None of these energies comes from a mysterious reservoir hidden inside the electron. Every bit of energy is traceable. Rest energy traces to mass. Mass traces to the Higgs field interaction. Kinetic energy traces to fields doing work. Potential energy traces to the arrangement of charges. Quantized state energy traces to the wave nature of the electron confined in a potential well. Photon energy traces to transitions between allowed states. And every transfer obeys conservation of energy without exception. The electron is not a source of energy. It is a carrier, a participant, a node in a vast network of energy transfers that spans the entire physical universe. It receives energy from fields and photons and collisions. It gives energy back through the same mechanisms. And at every step, the books balance perfectly. This is the physical chain at the heart of the story. The electron possesses rest energy because it has mass. Interactions place it within a particular potential or quantum state. Fields, photons, and collisions transfer energy to or from that state. The electron's motion or binding changes accordingly, and the total energy remains conserved across the full system, always, without exception, in every experiment ever conducted. The next time you flip a light switch and see a room fill with light, remember that the photons entering your eyes were emitted by electrons in the filament or in the semiconductor of an LED. Those electrons drop from higher energy states to lower ones, and the energy difference became the light you see. The energy those electrons had came from the electric current flowing through the circuit, which came from the power grid, which came from a generator or solar panel, which ultimately traces back to nuclear reactions in the core of a star or chemical energy stored in fossil fuels or the kinetic energy of wind or water. The chain stretches from the heart of a star to the photon striking your retina, and every single link is an energy transfer. Nothing appeared from nothing. Nothing vanished. The universe kept its books. That is where an electron really gets its energy from. Not from one place, not from one source, not from a mysterious internal supply, but from the physical universe itself, through interactions governed by the laws of physics, each transfer precise, each transformation accountable, each step conserving the total energy of the system with a perfection that has never once been violated in the entire history of experimental science. The electron is simple. It has mass, charge, and spin. But the energy story written around that simplicity spans rest energy and relativity, electric fields and quantum waves, photon absorption and particle annihilation. It reaches from the Higgs field that gave the electron its mass to the spectral lines of distant stars. And through it all, one truth holds. Every electron volt is accounted for. Energy is never conjured, never lost, only passed along from one part of the universe to another, in an unbroken chain that has been running since the beginning of time.